Welcome to August 25th LeetCode Challenge. Sum of squared numbers. Given a non-negative integer c, decide whether two integers a and b such that a squared plus b squared is equal to c. So we have example 1, c equals 5. So is it true that we could return a and b squared, the sum of the squares, such that this is true? The answer is true, because where 1 squared plus 2 squared equals 5. So another example here, c is equal to 3. Is there a sum of squares that equal to 3? The answer is no. Is there a sum of squares that equal to 4? The answer is yes. And that would be either, for example, you have integers, you have integers 0 and 2 plus 2, or you have 2, or you have, 0 and 2. Is there an integer, sum of squares that equal to 2? Yes, you have 1 squared plus 1 squared equals 2. Is there an integer equals sum of squares equal to 1? Yes, it'd be 0 plus 1 squared. So you have c between 0 and 1 to a very big number, and you want to write an algorithm to basically solve this. Is this possible? So there's a brute force approach as well to this, which I'm going to kind of do with the root function. So let's see, how am I best explain this? So we basically consider every single combination of a and b to check that the sum of squares is equal to c, basically. So now that a and b can lie within the range of 0 to basically the square root of c, so we need to check the values of b and a within this range. So that's pretty much it. Another thing we keep in mind is the square of an n positive integer can be represented as a sum of the first n positive integers. So using that means that, for instance, you could determine basically c has to be, and b squared, basically b squared has to be equal to c minus a squared, right? Using that rearrangement as well. So I want to use that notion to help us solve for this. So we'll go super easy, brute force first, and then we'll figure out another method as well. So we're going to iterate through for I integer in the range of the integer of the square root. We're going to use a math function here, math.square root, I guess. It's a bit cheating, but we'll save that for now. We'll develop another method later. Plus 1. So we will iterate through each of the numbers in the square root of c, right? Because we know that, for instance, if we bring b over to this side, we know that a squared is equal to c minus b squared. So therefore, the square root of a, or c, I should say, is we need to iterate through the square root of c. So we're going to say for each element j equal to c minus I squared. We're going to do if the integer of math.square root of j to the power of 2 squared, I should say, is equal to j. If yes, return true, else return false. And this should run code. Finish, submit. Excellent. So the time complexity for this is it's using this math square root function, which is actually it'll be basically using the time complexity will be big O of c, where c is the integer. So the total numbers of the sum is updated. So the square root function has a specific. We do actually know it's big we have a for loop here actually. So it'd be the big O of n times a constant, which is big O of n. For time complexity, space complexity is big O of constant space, because we just return true or false if the flag is true. Alright, that's pretty much it for this one using the square root function. There is a way to do it without the square root function, but I want to show you guys an interesting method here. It's called Ferments Theorem. So if you guys are mathematically inclined, you guys would know that the sum of squares numbers is this formula right here. There's actually a way of solving it using a mathematical approach using Fermat's theorem. So Fermat's theorem states that any positive integer n is expressible as a sum of two squares if and only if the prime factorization of n, every prime of the form 4k plus 3, occurs in even numbers of time. So it's a high-level math type of thing. If you guys are familiar with it, there's theorem includes, it's beyond the scope of, I guess, any normal regular type of programmer, but it's something good to know about. It's, I think, third or fourth year mathematics. But how it goes is that you want this prime factor. So the general form of what we're approaching is basically a squared plus b squared is equal to c. And we know that where a, if we assume that a is less than or equal to b, so this is the general form we're given. So that means that c is the prime factorization of c will be basically you need two numbers, call it p and q, I guess. P1 power of q1 plus p2 to the power of q2 dot 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 not plus times let's see, pk to the power of qk. So this is the factorization of c using Fermat's theorem. So if we use this approach, we can scan for each prime number factor within c. So we know that you see how a, so we know that the k here in this case is actually equal to 2, right? Because if you see this this pattern here, we're looking for k here, and k is a square, so that'll be k equals to 2. So I'm just going to say k is equal to 2. And while k to the power of k is less than or equal to c, we are going to check whether the factor or c or not is part of it's the exponent of the factor. So I'm gonna call this call it count, I guess, equals 0. And what we want to do is if c is a factor of it, so that would be the modulus of k is equal to 0, right? While c is a modulus of k. So check whether the factor or c or not is equal to 0. And then we want to get the current exponent of the current factor, right? We want to get the current exponent of the current factor. So we want to do, or k I should say, is equal to 0. Then we want to get that number. We want to accumulate the exponent of the prime factors. So that means that we want to increment our count, how many times that occurs, and we want to basically get it such that it's we want to basically divide it by c divided by k. Okay. All right. So remember that and we want to basically reject the factors from the decomposition form. So another way of saying this in math is basically 4k plus 3 to the power of q, as written before, is divisible by c, where q is an odd integer, right? So this is part of Ferments theorem. So in order to express this is what we need to basically find whether it's false or true. And to do that, we'll do if k is a modulus 4 is equal to 3, and the count, the modulus 2, is not equal to 0. Then we want to do is return false, because this is not what we want. We want to basically reject the factor decompositions of the form where q is odd. Next, we try the next factor, right? So factor will be incremented, so we want to change the factor. So that'll be k incremented to 1 by 1, right? So we have k being 2 here, which start with 2, because anything to the power of 1 is 1 itself, right? So we increment that, and then we want to return whether c is a modulus of 4 is not equal to 3. I'm just going to erase this a bit. Alright, let's run this. And down here we see that we reject the number of the form, basically c equals 4k plus 3, where k is a non-negative integer. Accepted. Alright, so that's using Ferments theorem. It's the time complexity is the big O of square root of c log c. So we find the factors of c using their count, using repetitive numbers of repeated divisions. We check whether k is within the ranges of 0 to the root of c. So the maximum time a number of factors k can occur is the basically log c times. And considering 2 is the only factor, where c is equal to 2 to the power of x. Alright, so let's see, let's write this out. C is equal to 2 to the power of x. So that means, using the logarithm identity, we have x is equal to log of c, right? So that's time. For time complexity, it would be big O of root c log c, and space complexity is return a boolean, so it's constant space. All right, there you go. It's a bit, the Fermat one is actually pretty neat and concise, but it requires a little bit of math, and I remember solving this using induction once. It was pretty mind blowing. All right, have a great day, guys.